lesson, we'll use equal weighted portfolio object from EUA futures, S&P 500, ESG fund and Bitcoin data to perform return and volatility modeling. First, we'll perform ARMA modeling and then find the model across several competing models that offers best out of sample prediction accuracy. Then we'll also model volatility using Garch models and find the most suitable model using AIC and BIC information criteria. In this video, we'll do a quick recap and show how to construct our variable portfolio, equal weighted portfolio variable for analysis. To begin with, recall in the previous lesson, we had 4 data series and we had saved this object by the name of final data. Let me show you how to read this. So I need to click on this final data object. If I click on OK, a command line will be run. Data is already read, but for record, I'll just keep this command line. In future, if I may forget the location and all, I can simply just press Ctrl Enter and this data will be read. In this data, let me show you what is inside this data. This carries 4 data points. One is time series of Bitcoin, S&P 500, ESG fund and carbon market, that is EUA. Now from this data, I'll first construct the return series. Let's see how. So first I'll create a zoo object. Zoo is a time series object which requires application of zoo libraries. Now I'll type this zoo command, final data, and out of this final data, the last 4, which is Bitcoin, S&P, ESG, and these are the objects of my use. So I am only selecting column number 2 to 5. Column number 1 is date, and now I'm defining, because this is a zoo object, it needs a date observation to construct the time series. So I'm giving the date object here, and this is now my zoo object. If I print this zoo object, let me show you. There's a very interesting object. Inside this zoo object, you would notice there's no separate column for time variable. The time is marked as a stamp on each set of observation. Like for example, here you can see 2013, April 2013 is marked 29th, marked for all these 4 observations. So now I have my zoo object. Let us create the return. So let me call it as final ret, and I'll take a log and then take the difference. So very useful command, diff log. So this command first takes the log of the object inside, which is final zoo, which has 4 price series. First it will take the log, natural log here, and then difference. So it becomes like natural log of pt upon pt minus 1, price at time t divided by price at time t minus 1, which is a property of log, that log of pt upon pt minus 1 is same as natural log of pt minus natural log of pt minus 1. So this is my return object. Now in this return object, I will construct my equal weighted portfolio by simply taking row means. For example, I'll run this final return dollar equal weight portfolio. So I'm creating this equal weight portfolio, which is nothing but row means. So I'm taking these means of these corresponding rows. Let me show you what is inside my final return object. I haven't shown that yet. So if you take the head, these are the return object. So notice these are all return observations for each row constructed from originally the price variable. So now I can take row means, and inside this row means I can type this. So essentially what will happen is all these returns, their mean will be taken, which is essentially equal weighted portfolio object is created. I am assigning equal weights to them. So this is my portfolio object. I can separately sort of save this equal weighted portfolio object as final return dollar. So now I'm extracting that equal weighted portfolio object from my original data frame final rate. In this process, some NA observations, not available observations may have been created. For example, when you construct return, the first observation is eliminated. To avoid such issues in one go, just using na.omit. This will help me removing all those NA observations. And now we have created our equal portfolio object. So to summarize this video, we have first read the data which contained all the 4 time series prices. Then in this data, we constructed a time series object, created a time series object out of the price data. Then we constructed the return from this data and took the equal weighted averages of these return, which led to a series of returns, which is sort of equal weighted portfolio. Then we clean the data, and now we are good to start with the operations. In this video, we'll start the exercise by setting the working directory, load the relevant packages, and read the data. So let us first set the working directory by clicking on Session tab here, set working directory, choose directory. Now I have already set my working directory where all my data and required files are there. So I'll just click on open, and a command will appear on my console window here. For future reference, I can copy paste this command here so that even if I may forget the exact location, I can see this and just run control enter, or by running this command pressing run. Either way I can press control enter or run this command, and then all the relevant files will appear on my file tab here. Next, we'll load the relevant packages. So in this particular lesson, we are going to use library forecast. Then we are going to use library Garch for Garch and all. Then we are going to use XTS. A lot of data we are going to convert into extensible time series. We are also planning to use tidyverse for some of its applications. We will use library zoo, and because we are going to measure some errors, RMSE, MSE and so on, we are also planning to use matrix. So this is, we have loaded all the relevant packages for the current working session. So now we are ready to read the data, and you notice as soon as I run my command on the script here, I'm seeing the same execution on my console window as well. So let us now read the data. I have the data file at my equi-weighted underscore portfolio variable. Let's use this read RDS, and by the same name I have the same file, this file. So you can see here this file is there. I could have directly click on it, okay, and the file would be read. That is one way to read it. I can just paste that command for future reference. For example, in future I don't want to exactly remember the name or anything, I can just press control enter and the file will be run. So this is how I read the data. Let me examine the data. So if I check the class of this equi weight portfolio, the class of this data is zoo, so it's a time series object. I can also look at the head of this, few initial observations. So these are my time series of portfolio observation, which is my equal weighted portfolio that I have created from my cryptocurrency, EAG fund, S&P 500 and carbon market data. So this is equal weighted portfolio of those data points which I have created in the previous lesson, the equal weighted portfolio. Let me also show you the plot of this equal weighted so we get a good idea how it appears. So if I plot this, I can run this plot command, and let me clean this. So if I run this plot command, you can see the plot of this equal weighted portfolio. It's there's some shock somewhere around 2020 due to COVID, and it's a fluctuating series. It's relatively less fluctuating because it's a portfolio thing. So to summarize, in this video, first we had set the working directory for our current session. Then we loaded the relevant packages. These packages were already installed, so I need not install them again. I have simply added them in the current working environment only. Then we read the data, which is equal weighted portfolio. This data we created in the previous session. This essentially is a combination of 4 series, which is one carbon market data, then cryptocurrency data, ESG fund data, and a broad market index like S&P 500. And I have taken their equal weighted, that is assigned them 25%, 25% weight. In the previous lesson, we constructed this data, and now we are ready to model with the Arma-Rima kind of models. In this video, we'll start with our Arma-Rima modeling process. So we'll start with the Arma-Rima modeling. First, we'll convert our time series object into extensible time series by using this as.xts command. This has very nice and desirable properties, and that's why we installed this XTS library. If I show you the class now, see the class that has changed. If you see the class of this new variable, that is XTS zoo, extensible time series. The plot will also be very nicely appearing. If I show you the plot, the new plot of this data, you can see a very nice looking plot with its time. Let me zoom it for you. So a very nice plot with all its properties is there. We can see some of the shocks in the series. Now in Arma-Rima modeling, if you recall our discussion about conceptual concepts, the first and most important part is construction of ACF PACF plot, that is autocorrelation function and partial autocorrelation function. This gives us the property or highlights the first visual examination about their Arma-Rima properties. So first, let me show you the ACF plot here. ACF plot of this ACF plot very nicely highlights. You can see the first bar 0, which is ideally 1. The next bars are smaller, which show that there is some minor autocorrelation, though it is significant because it is outside the dotted blue lines. So there are few of them that are significant, indicating there is some kind of AR structure. We'll have more details to see about that, but there is some AR structure that is visible here. Similarly, we can see if there is PACF. PACF highlights that very clearly because it so now this PACF structure has multiple lines, which shows that not only there is AR, there is some kind of MA structure also happening. So let us look at this AR, ACF and PACF structure in conjunction. So we can see there is a sort of declining kind of structure in the PACF diagram, and if you look at PACF, there are few bars. So there is, it seems to be the presence of both AR and MA, because if there is AR, then that AR structure is nicely captured by PACF plot in the form of declining, this kind of declining bars, as you can see here. Similarly, if there is MA, you can see in the ACF plot this kind of declining structure. There is somewhat small MA, but predominant, you can see. So you can see the some kind of some AR. If there was strong AR, then you would have strongly large bars across the legs, but some AR. But the same time, if you look at PACF, that confirms the presence of MA structure. So we have some intuition that there is MA AR structure taking place. Next, we'll try to see the box plot, the Lung box and box PS plot for test of autocorrelation. So we'll test with Lung box and box PS test to see if there is some kind of autocorrelation structure. So first is box dot test, and I'll run this equal weight portfolio object. So let's say I have some intuition that there's some lag structure, so I'm putting a lag of 4. You can change the lag size. My hunch is because these markets run at least a week, so there, even if there is some information structure, that should be captured in a weekly interval. So because of that, I'm putting as 4-day lag. If I run this, you can see it is significant, so that means there is some autocorrelation in the process. Autocorrelation structure is indeed present. I'll make another text, which is Lungbox test in this same lag 4. So even if there is 4 lag, obviously the 1 lag also would have been significant. So let me show you. See, it is also significant. So 1 lag structure is also significant. Whether you use 1 or 4, it is turning out to be significant. So there is indeed some kind of Arma-Rima structure. In the next video, we'll run auto.arima command and simulate that structure. In this video, to summarize, we saw through ACF PACF diagram that there is some visual intuition that we have some kind of ARMA structure there. There is some, particularly from PACF diagram, we found that there is some AR structure, and from ACF diagram, we found there was some MA structure, presence of some significant MA, though the sizes are small. Based on this, we also tested them for autocorrelation of through box test, box Pierce and Lungbox. We have found there was some evidence of significant autocorrelated lags. In this video, we'll start with the examination of data and then segregate the data into training and test data. First, with the help of auto.arima command, which is an inbuilt command, it is available in the R package auto.arima. It's a very useful command. So if you run this command, you will see this is available in the forecast package. It helps simulate or find the inherent structure in the process. So if I run this auto.arima to understand this information structure. So if I run this auto.arima command, In this auto.arima command, if I run this equal portfolio, you can see it tells me that there is some kind of MA5, MA3, AR5, autoregressive, 5 autoregressive terms and 3 MA terms are there in the process. So that gives me some idea that it is AR5 and MA3, that is ARMA 5,3 process. So if that is the case, then while simulating our process, we'll take care of that. Now let us first break the data into test and training data set. This is very important. So you first train the model on the training data set and then you see whether it has good out of sample prediction through testing data set. So first we'll check the accuracy of model through in sample forecast by using training data set. So let's see, let's create the training data set. For that, I'm segregating this equal portfolio object into two segments. One is starting from 2017 Jan to 2020 December. This is my training of data. So this is my training data from 3-year data. It's a 3-year data, training data. So I'll train my data on this object. Equalate portfolio train. So this is my training object. Similarly, I can also construct my testing object from where whenever I have to test or test the model for out of sample accuracy. So this is in the training data, if you will test, it may fit very well, which is the problem of overfitting. So I need to test my data outside that or through a new data, new sample on which it was not trained. So it is not aware about that data and therefore its power or accuracy will be tested. So I am using for 2021 and 2022 2 years for, sorry, I should use testing the data here, test. So first is my training and this is my testing data. So now I have my training data set available with me and I need to do the forecasting and then test them. So first I'll simulate the model, using test, training data. So I will start with a very simple kind of ARMA model. Let's call it ARMA M1 model, and in this ARMA model, I am giving a very simple kind of specification. We'll increase the complexity. First, I am giving it order C equal to C101. So on this, in this model, we are only using one lag of AR, which is this one, and one lag of MA. So this is a very simple model. If I print it for you, you can see ARMA, it's a simulated model given this data. So we simulated this. Here you can see the output. Similarly, you can simulate M2. How do we simulate M2? This is, let's by assuming two AR and two MA terms. So this is M2. I can print M2 for you. Let's print M2 now. So you can see M2. So this is two AR and two MA terms. Earlier we started with MA1, then I can also do with M3 where we'll use 3. Now the model has become more complex. So this is M3. Let's simulate M3. Similarly, so my plan is to simulate 4 such models. So this M4 will have 4 AR term and 4 MA term, and I can just, you can see this, and then fifth model with 5 term. Now this has become extremely complex. The sixth term we'll use, which we simulated from, so recall we simulated through auto.arima, and in this auto.arima we found that there are 5 AR and 3 term. If you recall, let me show you again auto.arima. So when we ran that auto.arima, you would notice there are 5 AR and 3 MA terms appeared. So now the last model M6 would have the last model M6 would have 5 AR and 3 MA term as we simulated in the auto.arima command. Let us print it also. So we can see the object here. So this is the output. There are some NAs produced, that means slightly it is giving me slightly poor fit. That usually happens when mathematically a model is very good fit, but theoretically it is not justified. Then this kind of situations may appear where mathematically it was giving me a good fit, but when I fitted the 5-3 model AR5 and MA3, it is giving me NANs for my standard error. So that means there is some challenge while fitting this kind of structure, but we'll go ahead. So to summarize, in this video, we broken our data into test and training set. Then we simulated 6 different models, including for each lag of ARMA 1, 2, 3, 4, 5. And lastly, we also simulated a fitted structure, mathematically fitted structure. So to auto.arima command, we named it M6. So we have 5 model that we have trained. And in the next video, we'll examine their out of sample accuracy. In this video, we'll examine the in sample fitting accuracy of our model. And for that, we have already trained our 6 models. We'll examine which one of them fit in sample data very well. Please recall, AIC-BIC measures are very useful measures for such examination, as they penalize addition of new variable unless until these new variables are giving us a very good information content or adding to the information. So I'll create this output object to store these fitted AIC-BIC values. So it's a data frame object with two rows each for AIC-BIC and 6 columns for all the 6 models respectively. Now I'll give the names of these columns as M1, M2. So these are my column names that I'm giving. M3. For each column there is one M4, then M5, then M6. So these are my column names. Similarly, I can give my row names also. I can give my row names, which are AIC, BIC. So let me show you how the print this object and show you how this object is appearing on my console. So there are 6 columns, each named M1, M2, and 6 rows, each named AIC, BIC. 2 rows basically, each for AIC, BIC. And now I'll start assigning the values in each of these row columns. So first, the simple way to do this is pick a column. Let's say first column is M1. Then I extract the AIC value from M1 model and also BIC value from M1 model. If I run this command, the first column, M1 column, is assigned these AIC BIC values. In an identical fashion, I can do the same for M2, M3, M4, M5, M6. So now I have my AIC BIC values nicely assigned to this output object that I had created. You can see here. If I print this, you can see these values are printed. Now I would not like to sort of manually compare them. So what I'll do is I'll create a rank object which will rank these values. So let me show you how it is done. It's very simple. There's a very interesting rank command which will help me choose the right set of objects. For example, if I do rank output based on AIC, so this will give me the rank based on AIC. So this gives the first rank to M5. Notice this rank, the way it works, it is giving the highest rank to the lowest, the one to the lowest one, which is -5307. This is the lowest value and it is giving the rank first. And this is the most complex of all. It contains 5 AR and MA terms. And if I run BIC, BIC gives the rank 1 to M1. So that is interesting. On BIC, we are getting the first rank with M1, while which is the simplest model, while AIC is giving the highest rank to M5. Now, this may be due to the fact that BIC penalizes addition of variable more heavily. So the key difference between AIC BIC in their formula is that BIC penalizes additional of new variables more heavily unless until they contribute very significantly to information. So this tells us that contrasting results we are getting. A as per AIC, M5, which is 5's ARMA, M5 which is ARMA 5 model is good, which is more complex, while as per BIC we are getting that M1, which is ARMA 1,1 model, is best. So more testing is needed, and to summarize, in this video we created an object that stored our AIC BIC values. We examined the AIC BIC values for in sample fitness, and we found very contrasting result. While AIC showed that M5 is the best and M1 is the worst, which was the most simple, while the most complex M5 was the best, BIC showed that M1 was the best. So we ascribe this to the fact that BIC penalizes addition of new variables more heavily unless until they contribute to the model. However, we must note that often in sample fitting is vitiated with the overfitting process. That is, a given model in which it is trying to fit the data. Often more complex models, they overfit the given sample in which they are trained, but their out of sample performance is not so good. So in the next set of videos, we'll try to conduct out of sample fitting of the data and see which model performs well. In this video, we'll construct out of sample forecast, out of sample forecast. Why this is important is because often a model which fits well in a given sample has a poor out of sample forecasting accuracy, and particularly the more complex model are prone to this problem. So we'll conduct the out of sample forecast and then we will visualize them also. So visual comparison, we'll see how they are performing. So for this, let's create this m1 underscore predict object, and we'll assign in this predict command, we'll predict for 50 periods ahead. Now this is a critical choice, what period or what length you want to predict. A very small period would result in very few observations where you cannot very effectively test the performance of your model. In contrast, if you choose very large number of observations, then after a certain point your forecast will become meaningless because no new information is added. So I feel that 50 steps ahead forecast is a reasonable compromise, a reasonable trade-off between synchronicity and accuracy. So a period that is not too small, neither too large, and effective to judge the model. So then similarly for M2, for all the models we will predict next 50 steps. So we have these 6 models that we have employed for prediction: M1, M2, M3, M4, M5, M6. Let us start with the visualization. So I'll create this equal weight portfolio predict object, which will contain, it's a zoo object, it will contain all the predicted values, and inside this I need to have a C bind. So first is the actual set of observations. What are these observations? So these are from test data set and we are using the first 50 observations to compare. So first 50 observations. Then I have prediction from my M1 model, M1 which is equal to M1 underscore predict, and inside predict the object is stored with pred. So here I have to use this pred object. I'll store them. Then M2, in the M2 column, I'm giving the column name as M2. In M2 column, the predicted values from the M2 model will be there. So I'm filling those values. Then M3 will have, so I can do that. I need not type the entire thing again and again. So then we have M3. So this consistency name is very useful. You don't have to write the full thing again. You just copy paste and make use of your already written command. Then similarly you can have M5 and then M6. So this is the data frame. Now this is my data frame object, and now I need to provide the date index that will be used. So I'm going to use the index object from my equal weight portfolio test data and initial 10 dates, as we are testing against the first 10 observations in the test data. So this will be run. So let us run it. So once I run it, I can check the object produced. It should be a column. So let's say head of this, let us run the head of this. This should be a zoo object with 50 observations. I can check the dimension of this object also. So the 50 observation with 7 columns. First column is the actual observation, and then remaining 6 columns are predicted. So now very easily let us plot this object. So for that we'll make use of plot command. Equal weight portfolio predicted object. We'll give the central heading as visual comparison across models. We want to make this heading a slightly higher in size, so sex.main will give us 2, so that larger headings will result. Each line, each plot should be of different color. So this call object, line width has 2 and type as B, so both line and point type, both point and line will appear. Lastly, I am giving this PCH, very useful argument, PCH as 1 to 6. So each graph will have a separate symbol. So the points will be of separate design or separate object for point. Let me show you what exactly I mean here. So if I run this, notice a very nice looking plot has appeared. In each plot, you can have model M1, M2, M3 and so on, M5, M4, M6, their predictions and the actual object. And you can see all of them are different color, and not only different color, the point object, the point that is there inside line is also different. So it's a very nice plot. And later on we'll see which is more accurate here. You can see M1, M2 being very simple. After a few steps they converge to a straight line, while M3, M4, M5, M6, which are more complex, are giving some fluctuations, have some fluctuations which gradually die away. So to summarize, in this video we first constructed 50 out of sample forecast, and then we visualized the predicted objects from different M1 to M6 models that we have simulated earlier, the trained earlier, and those predictions, and we also compared those predictions that were made using these simulated and trained models. In this video, we'll examine the out of sample forecasting efficiency of our trained models. For this, we'll first create an error object to store a number of errors. You can have as many errors as possible. We'll take a certain number of errors that are most often employed. Error object to compare the models. So first let me create this error object, which is a data frame kind of object. It contains 4 rows, each row for kind of error. We'll also create a complex error object using our computed error. So, and then we have 6 columns, each column for a model. First, we'll give the column names as we did earlier. So the column names would include corresponding to each. I need not type this, I can simply borrow this from the previous. So this is these are my columns. Each column represents one model. Similarly, I can have error value. So I am planning to use RMSE, which is very important error measure, root mean square error. Then MAE, mean absolute error, MAE. You can examine their construction on net, or you can go to this matrix package. For example, you can go to this matrix pack, or rather you can do this RMSE, and you can see the construction of each. It is part of matrix package, so you can check the documentation here. Also, you can have a look at the matrix package. Go to the package tab, search here the matrix package, and click in this web symbol and see whatever all the errors you will find there, their explanation and detailed computation. So we are not doing that right now. Then you have RMSLE. For example, this RMSLE, you can just press Control Enter here and see root mean square log error, its construction and everything. Lastly, we'll also create a complex error object. In such algorithmic systems, you often have an error which is a combination of all the errors which is desirable to you, and you see the performance of all the models on this particular error object. So you examine all the models, their performance on this complex error object. So let's create this error object. Let's print it. What do we have in this object? So if I print it, let me enlarge the console window. You can see here it has 6 columns, each corresponding to a model and each row corresponding to an error object. So next step would be assign the error values computed from our prediction models and store here. So we'll start with the first model, which is $M1, and first 3 errors we are computing. In the 4th error we are taking a simple average. As a simple system, we are taking a complex error, this complex error, as a simple average of these to avoid any such complexity right now. So first is RMSE. In this RMSE we'll compare the M1 predict object. This is our predicted object, and we'll compare it with the actual value. What is our actual value in the test data set? So in our test data set, the first 50 values we are comparing with the predicted 50 values. Similarly, like RMSC, I can have my other error object, which is MAE. So it makes the job simple. The similarity of codes makes it easier to copy paste. So the next error object is RMSLE. So we have 3 error objects we have created, and this is for model M1. So let me run it. Let me see if it is error free. So if I have run it correctly, I can print my error object now. Let's see. Yes. So first 3 errors are assigned. This means I have run the command correctly. Similar fashion. Now, before moving to the next model, I need to also generate the last value. What is the last value? Value number 4, which is nothing but the complex error or the mean of all the error objects, which is mean of this object that I have created, mean of this. So if it is running error free, let me show you the error object. Yes, all the 4 values are filled, so we are good. So the same command I need not write again. I'll just copy paste it for the other objects simply by replacing M1 from M2. And if I replace it, the model will be good to go. Similarly, I'll again paste it and replace M1 by M3. This makes coding very easy. Our job very easy, otherwise typing would have taken a lot of time here. So I'm just copy pasting the same command, only changing. And if you maintain consistency with the symbols, this is the great advantage that you have. You don't have to write everything again. You can just simply copy paste due to similarity and this aspect. 4 with 5 now. So every time I'm replacing this L5, then lastly 6. So we have replaced now all 6. The next step is to run these commands. Let's run them again. So starting with 1, I'll run them again. So now my error object will be completely filled with all the 3 errors, that is RMSE, MAE and RMSLE, along with the complex error object. Let's see if it is done or there's some error. So all the error objects are filled. So in this video, we computed our error object to fill the performance error of all the 6 models. On RMSE, MAE, RMSLE error, and we also created one complex error object, which is nothing but simple average of all the objects. One can create a complex error object with much more complex function of the errors computed. In the next video, we'll compare the models, their performances across these error objects. In the previous video, we have computed the error measures of our fitted object. In this video, we'll compare the errors and thus the performance of M1 to M16 models. So we'll create a rank object. This will rank the performance on all the error objects that we have created. So this object will have 4 rows corresponding to each error measure, that is RMSE, MAE, RMSLE and complex error, and columns ncol, that is equal to 6. So 6 columns for each models, 1 column for each model. So let's have, again, this is the same scheme that we had earlier. Call names, we'll have the rank object and we'll use the same call name. So I'll just copy it from our previous code. I have these 6 models, and similarly I will have row names, and each row corresponds to a error measure. So I'll just use this previous command as here. So now if I run this, the rank object that I have created will have row columns where each column is the model and each row is the error. Now all I need to do is fill this rank object with ranks. So now we'll fill this rank objects with ranks computed from the error object. So we have an error object which we'll use to rank these models, and if I run this, the rank object is assigned. So let's compare the rank values produced from the with the error value. So let me show you. So let us compare. Notice that on RMSE, if you look at RMSE, M5 performs best. So on RMSE, this 0.10195 is the best. Across all the models, M5 is best on RMSE. Similarly, if you look at M3, it is worst on all the errors. M3 is worst on all the errors across all the models. So that way we can see different objects, and particularly object M2 on our desired objective function complex, which is complex error, M2 works best. So you can see here M2 0.0183 is better than all the objects here, and therefore it is our model of choice, M2, which is second order AR and second order MA process. To summarize, in this video we compared the ranks of our error objects, errors from different models, and we found that different models work or rate perform differently in different error objects. But on our desired complex object, which was the average of all the 3 errors, RMSE, MAE, RMSLE, M2 works well. We have an intuition for M2 working well as it is a very sort of parsimonious object. It has only 2 lakhs of AR and MA structure as compared to M3, M4, M5 and M6, which are more complex. At the same time, it is not as simplistic as M1, so it is slightly better than M1 and performs well on our complex error object. In fact, it performs well on MAE object also. In the previous video, we discussed the modeling of return and out of sample prediction and forecasting. In this video, we'll talk about modeling the volatility, and for that we'll employ the Garch models. Garch modeling for volatility. In particular, we are going to use standard GJR and EGAR, that exponential Garch, and 2 kinds of assumption we'll assume, normal and generalized error distribution, GED. So we'll do the Garch modeling with these specifications. For interpretation and theoretical underpinnings, we can refer to the theoretical lectures that we did in the previous weeks. So we would be needing, for comparison of these models, we'll be using again information criteria. In particular, we'll be using AIC, BIC, Shibata, Hanqing, and a complex information criteria object. So let's create this information criteria object that we are going to make use of. In this, we'll have 5 rows, each row representing one information criteria like AIC, BIC and so on, and 6 columns, one for each of the models. Let me explain what are these models. For all the theoretical underpinning, we have already discussed in the previous week, so in the interest of brevity, I'll not repeat it again. So we'll give them the names. So first we have standard Garch with normal distribution. We'll assume the normal distribution. Then we'll have GJR Garch with normal distribution. Then we'll have E exponential Garch, again a very powerful model with normal distribution assumption. Similarly, we will change the distribution to generalized error distribution, which is a more realistic assumption. So the same set of models, standard Garch with GD, generalized redistribution, GJR gauge with generalized redistribution, and exponential gauge with generalized redistribution. So these are the three other versions. So let me also set up the row name. So now in this case, the row names are according to the information criteria that we are going to use, which is AIC, Kaike, Bayesian, BIC. Then we have Shibata. We'll use Hanquin, HQ, which is HQIC or HQ, Hanquin. And a complex error of complex information object, which simply is in this case we'll be using a simple average. You can have any complexity that you want, a more complex function of the remaining four criteria. In this case I'll be using, for simplicity, the simple average. Now I'm going to plot my predicted volatility, so I'm setting my plot window as mfro equal to C32. This command will ensure that my plotting is done nicely, so all the six fitted volatility from all the six models are nicely fitted. So let's start. So first I'll start with the simple standard gauge. First we'll model the normal distribution assumption. Three models are there. First one is the standard gauge. So first one is the standard gauge model. This requires application of ru-gauge package that we added to our current working session earlier. So all you need to do is type this gauge spec. So this will create your spec function and spec object. You have gauge spec object. So this gauge spec function will ensure that your mean model. So our mean model is list, and already we have found the right fit ARMA model. So ARMA order equal to note that we already found that 2,2 ARMA model fits well, so we'll be using that. Then we also need to supply with the variance model, which is, in this case we are going to use standard gauge. So list model equal to S gauge, standard gauge model. In this case the distributional assumption is normal, so we are providing distribution as normal. So later on we'll also be using generalized error distribution. So we'll run this command to see if it is running error free. Yes, it does. So our gauge spec object is there. You can also print your gauge spec object. So you can, if you want, you can print your gauge spec object. It gives you a lot of information. For example, it gives you the kind of model you have run and basic contours of the model. Next, we'll fit our data in this specification and we'll create a new object called gauge fit, which will comprise of ugauge fit. We'll fit our data. So use this ugauge fit, and data we already had, which is equal portfolio test object, equal weight portfolio test object. So this is our test data which we are going to fit, and then we'll use our spec as gauge spec. So this spec we have created, it may take a few seconds to fit this object. Once the object is fitted, you can print it also to see what is inside this object. For example, it contains a lot of information for us, starting from, it gives us the parameters mu, AR1, MA1, MA2, omega, alpha, all those parameters. For interpretation, you can go and check the lectures, what are the interpretations of these estimates. It is also there with robust standard errors, so you can check the interpretation of these parameters and their implication for the model. We have in these information criteria that we are going to extract. There are some other tests, for example, Lungbock text that we have already discussed about the autocorrelation structure, ArchLM text for arch effects. You can check whether arch effects are there. Particularly in this case, it seems that not many arch effects are there, which may be the case that we are using a very diversified portfolio, so probably some of the arch effects are eliminated. So all the properties you can have a look at the theoretical discussion. So we are not going to discuss that. The next step is to extract the fitted vol. So let's extract the volatility, conditional volatility that we have computed with the sigma command, gauge fit. I can extract it. For now, you can print it also. So these will be fitted volatilities. If you want, you can print this as well, plot fit. So here I can plot this object with plot fit. I can give the central heading as mean equal to standard norm, and I'll change the colors so that plot is differentiable. So you can have this fit wall and it is plotted here. So that way you can plot. So what I'll do is I'll run this command so that, because we have 6 plots that are going to come up, so it should be there. So this is one plot. I'll plot them simultaneously. The next step is to save our fitted object, the AIC-BIC criteria from 1 to 4 in our information criteria info criteria function, and I can fit the gauge fit object. This will save my information criteria here. Let me show it to you. Let me print it. So if I print it, yeah, you can see here. So now I have shown you how to create my fitted AI object with AIC-BIC criteria extraction, and we have also visualized the volatility here. I'll create the remaining 5 models and show you, summarize the findings in the next video. Now in this video we'll construct the remaining 5 objects, but before that, if you wanted to forecast using this gauge fitted model, all you need to do is you can create a gauge forecast kind of object by the name of gauge forecast, and you can use this ugauge forecast, provide your fitted model gauge fit, and whatever the step you want to forecast ahead, you can specify 5 period, and then you can print the forecasted objects. So you'll get the forecasted objects here, the forecasted series of sigma. So now we'll fit the remaining 5 model. The second one is GJR gauge model. So let's do the GJR gauge model. I'll not rewrite the entire code, so I'll just copy paste here. I'll just copy, and in this all I need to do is, in this instead of this I can mention this GJR. The rest of the things will be taken care of automatically. In the name also here I'll write GJR. Then here I need to change as GJR norm. Similarly, we have next exponential gauge or E-gauge, exponential gauge. For that again I need to write E for exponential gauge. Again here I'll write exponential, and I need to change here also with E norm. So this is my exponential gauge model details that are used. Then the next, after this I have created 3 specifications. So now I'll use generalized error distribution. So I'll use generalized error distribution assumption, and I'll fit the remaining all 3 models. All I need to do is, in the same set of model, I need to here change SGD as GD. Also I need to change here as plotting, and then here GD. Similarly here I need to use a generalized error distribution, and here also instead of normal I'll use GD, and here also I need to use GJR GD. Lastly here also I'll change to SGD, and this also norm also the plot colors that I have used, I need to change them slightly. For now I have used the plot color. Here also I'll change to EG. Now the plot, this is the 6th plot, so color 6. This is the 5th, so color 5. Then color 4, color 3, color 2, and then last color 1. So now I'll run them all at one go, and I'll clean my plotting window so that nice plot is there. So let me run the full thing in one go, starting from here. Let's see if it runs error free. So yep, it seems the graphs are being produced. You can see very nice graphs are being produced. Error is not there. It may take a few time because Gauge takes some time in extraction. Now let me zoom it for you. So this is my complete plot. All the 6 models fitted volatility, which is first is standard normal, then GJR Gauge with normal distribution, exponential Gauge with normal, standard error Gauge, GJR with generalized error, exponential with generalized error. Now there are some minor differences and we get slightly different volatility predictions here. We need to make use of AIC-BIC information criteria while ranking them, which we'll do in the next video. In this video, we'll at the end now, we'll just compile the last complex error object. And please note our complex error object, I see dollar, the fifth row, we said that it should be the mean of all the AIC-BIC criteria, column means for all the 4. So all the 4 rows, first 4 rows, I'll compute it. So let's see if it is done correctly. If I print this object, we can see, yes, we get all the error objects for our different models. So you can see here all the AIC, BIC, Shibata, Hanko complex and all the objects are printed here. We can also see the visual comparison of them. So in this video, we created and fitted our Garch model for 6 different models, particularly 3 distributions, normal, 2 distributions, normal and generalized error, and 3 different models, Garch model, that is standard, exponential and GJR. So we have 6 models we fitted, we extracted their information criteria, and we also visualize the fitted volatilities. We also saw how to predict in future steps, 5 steps, how to predict volatilities for next 5 steps. In the next video, we'll compare the rank of all these 6 models on their prediction, on their fitted volatility, how good they are fitting using these information criteria, and conclude the exercise. In this video, we'll compare the performance of our fitted 6 Garch models and rank them based on their information criteria. So we'll create a rank object. We need to create a rank object. So this rank object will be a data frame, as we are doing rank object. And it should have 5 rows for each information criteria, AIC, BIC, Shibata, Hanko and complex, and 6 columns for each of the 6 models. I'll borrow the names from the previous command. I'll not rewrite everything again, so I can borrow it here, the call names, and I'll just change it to rank variable. So rank and rank. So let me just print it out for you. So if I print it, you can see there are columns for each of the model, S norm, GGR norm, and so on, and information criteria, AC, BIC, SIC, and so on. All I need to do is just put the rank and use the rank function. Apply this rank function using this apply command. Apply this rank function on the information criteria object on its all columns and print it. So first I'll print this rank variable and I'll also print the IC variable so we can understand this ranking. So here the lower the information criteria, the better. So for example, here it seems that exponential GD is working best. Let's compare. So if you look at any version, the exponential GD seems to be the lowest across all the errors. So the lowest information AIC, BIC criteria are found in EGD. So in this case, the lower the information criteria, the better. And we can see the lowest is being produced by exponential GED Gauge. So that is the best model that we have. So to summarize this video, we have compared the performance of all the Gauge fitted models on different information criteria. We find that the lowest values, lowest information criteria values, that is the best fitted values, are obtained for all the 5 models, including AIC, BIC, Shibata, Hanko and complex on GED, exponential GED, so which is an X-metric model which gives us the best fit. To summarize this lesson, first we prepared our equal weighted portfolio object using the return series data of carbon market, Bitcoin, ESG fund and S&P 500 securities. Then we examined the object with ACF and PACF plots to find its ARMA properties. Next, we break the data into two segments, namely test and training datasets. Subsequently, we fit various ARMA models with different lags of AR and MA terms. We examine the sample goodness of fit for all these models with training dataset using AIC and BIC information criteria. Then we also examined the out-of-sample forecasting accuracy of these trained models on the test data with several error measures. We find that the bulky and less parsimonious models that attained high in-sample fit are not necessarily good fit in our out-of-sample predictions. Lastly, we model the volatility of our equal weight portfolio object using standard GJR and exponential gauge objects and assuming normal and generalized error distributions for the data. We compared the goodness of it across 6 gauge models, that is 3 gauge models and 2 distributional assumptions. We found that the exponential gauge model with generalized error distribution offers the best fit. We also plotted the fitted conditional volatility and performed volatility forecasting for our fitted volatility models.